Hi everyone, my name is Sneha Padmanaban. I'm a fourth year neuroscience major and my project was under the guidance of Dr. Ilana Bennett. So what is Alzheimer's disease? Alzheimer's disease is a debilitating neurodegenerative disease characterized by the accumulation of beta amyloid plaques and tau tangles in the brain. It's projected to affect 13.8 million Americans by the year 2060. The picture shows a comparison between a normal brain and a brain with Alzheimer's disease. In the Alzheimer's disease brain, the ventricles are enlarged while the cortex is shrunken down due to neurodegeneration. Neuroinflammation is the proliferation and swelling of microglia and astrocytes, which may be detected using diffusion-weighted imaging measures of underlying tissue structure. During any disease state, including Alzheimer's disease or AD, neuroinflammation is present. It's now believed that neuroinflammation may play a role in AD as neuroinflammation may result in response to beta amyloid plaque and tau tangle accumulation or as a separate etiology. There are many ways to measure inflammation, including blood and fluid markers, PET scans, and MRI. A relatively novel method is DWI, or diffusion-weighted imaging, which is a type of MRI, which assesses tissue microstructure via Brownian motion of water molecules. As DWI is sensitive to the movement of water molecules, the measures can indicate when tissue is degraded or when glial cells swell. As mentioned earlier, blood and fluid biomarkers can be used to assess neuroinflammation. Here we focused on STREM2, or soluble triggering receptor expressed on myeloid cells 2, which is a blood and fluid-based inflammatory marker in microglia. When microglia are activated, a cascade occurs which cleaves TREM2, which is a receptor present on microglia, into STREM2, and therefore STREM2 allows us to know if microglia are active and swollen. This picture represents the actions of microglia with respect to acute versus chronic inflammation. Normally, there are a few microglia surrounding the extraneurite space, and they are healthy with no enlargement. With acute neuroinflammation, more microglia accumulate in this space. With chronic neuroinflammation, the microglia become more enlarged and swollen, and their processes become shorter, allowing for more water diffusion. So utilizing these measures, we examined the corpus callosum because it's a white matter tract that functions in relaying information between the two hemispheres of the brain, and it's known to severely degrade during Alzheimer's disease. Accumulation of beta amyloid plaques in the corpus callosum creates glial cell imbalance and therefore disrupts its integrity. In this picture, it shows an image of the corpus callosum and the different subsections of it, and I specifically looked at the genu, body, and splenium. So little is known about whether diffusion measures of tissue microstructure correlate with neuroinflammatory markers, in this case STREM2. Therefore, this study examines the relationship between STREM2 and diffusion in the corpus callosum. We believe to see a positive correlation between STREM2 and diffusion, as higher diffusion is expected in regions with glial swelling and neurodegeneration. So for my material and methods, I had 40 participants, 20 controls, and 20 AD participants, and the STREM2 and diffusion imaging data was downloaded from the Alzheimer's Disease Neuroimaging, or ADNI, database. In our control group, we had 9 females whose age average was 72, 9 males whose age average was 76, and 2 unknown. In our AD group, we had 7 females whose age average was 69, 12 males whose age average was 78, and 1 unknown. Quality control was done at each pre-processing step. Brain extraction tool, or BET, was used to isolate brain tissue from non-brain tissue, and a mask was created to ensure that the following pre-processing steps will be restricted to just that area of brain tissue. Eddy corrections were performed to correct for eddy current distortions and participant motion. DTI fit was done to estimate the tensor at each voxel. We used a region of interest, or ROI, approach to analyze the data. A mask for the genu, body, and splenium portions of the corpus callosum was created, and an example of this is in the picture. This mask was defined using a standard atlas with the FSL mats command. FLIRT was done to register the corpus callosum mask from the standard space into each subject's diffusion space. We will be using between group t-tests and correlation analyses to compare the diffusion metrics in the corpus callosum of the controls versus the AD participants. Neuroinflammation was assessed using blood and fluid-based inflammatory markers from microglia, as mentioned before STRUM2. We will be specifically extracting fractional anisotropy, or FA, and mean diffusivity, or MD, values for each section of the corpus callosum in each participant group. FA is a measure of the amount of restricted diffusion in white matter tracts, meaning that a larger value would indicate more restricted diffusion. MD is a measure of overall diffusion, and higher values suggest more diffusion. So after conducting independent sample t-tests between the control and AD groups in STRUM2, I did not observe any statistically significant results, as the p-value I obtained was 0.81. However, when this test was performed with a larger sample size, significantly higher STRUM2 and significantly lower diffusion in the corpus callosum in the AD group relative to the controls was observed. And this was a completely different experiment. And the graph displays the results of my experiment. These are the results of the three sections of the corpus callosum, the genu, body, and splenium, and the group differences between AD and control participants. In all three sections of the corpus callosum, we observed that FA was lower in the AD participants compared to the controls, as observed in the graph on the left. Additionally, MD was higher in all AD participants compared to the controls, as observed on the graph on the right. The results were statistically significant for all of the groups except for FA in the splenium and genu. Based on the FA values, this can be interpreted as if there was less restricted diffusion in the corpus callosum of the AD participants compared to the controls. The difference in MD values translates to greater diffusivity in the AD participants. These results suggest that there's more neuroinflammation happening in the AD group compared to the controls, as there are greater rates of diffusion. Increased MD suggests that there's more free space within the cellular space, and this can mean that the diffusion measures of tissue microstructure are sensitive to similar neuroinflammatory processes as blood and fluid-based markers, and may provide insight on the progression of neuroinflammation in the corpus callosum during AD. Lastly, we conducted correlation analyses to examine the relationship between neuroinflammation measured with STRUM2 and these diffusion rates, FA and MD. With FA, we noticed negative correlation with STRUM2 as observed with the negative Pearson's R value. However, only the splenium values were significant. With MD, there's a positive correlation, and the body and D values were significant, while the genu values were marginally significant. Additionally, these statistically significant values were driven by the AD group, as correlation analyses conducted with the control group alone did not have any statistically significant relationships with STRUM2. These graphs display the scatter plots for statistically significant correlations received between diffusion rates in STRUM2, and the table represents all the p-values for each group. So we concluded that there's worse diffusion in the corpus callosum in AD participants. Some limitations would be the relatively small sample size, the region that we chose, and the access to data, as the ADNI database does not have a lot of the DWI data that I can extract from. My next steps would be to assess these values in a larger sample size to observe if I can obtain statistically significant results, especially in regards to the FA values in the genu and splenium, as well as the correlation analyses. Additionally, as there are several white matter tracts in the brain that may be affected by an Alzheimer's disease, it would be best to observe these differences in neuroinflammation of other white matter regions. These are my references, and thank you all for listening to my presentation.
Great, thank you, Sneha.